Hi, hello. My name is José Matias. Welcome to my talk. The title of my work is Real-Time Optimization with Persistent Parameter Adaptation Applied to an Experimental Rig. The work was developed at the Norwegian University of Science and Technology, but it's a collaboration with the University of São Paulo in Brazil. Here is a brief description of our paper. The main objective was to use two model-based production optimization schemes to solve a limited resource allocation problem using two different methods, the classical two-step RTO and real-time optimization with persistent parameter adaptation, ROPA. Here is a simple diagram summarizing the classical two-step RTO. This method, as the name indicates, is based on two steps. First, you adapt the model to the current plant state, then you use the updated model to optimize the plant. Since the two-step is based on steady-state models, we need to wait the plant to reach a steady state before updating the model. This steady-state detection step is one of the biggest shortcomings of this classical structure. Steady states are usually hard to detect, and the steady-state detection algorithm performance is highly dependent on users' input. As a consequence, the performance tends to be conservative, and the two-step RTO is not executed very often, decreasing its potential benefits. ROPA, on the other hand, appears as an alternative since it replaces the steady-state model adaptation step by a dynamic model adaptation, in which, for example, an extended Kalman filter is used for adapting the parameters continuously. Consequently, we don't need to wait for the system to reach steady state before triggering the optimization cycle. The same method has also been named hybrid RTO. They were both simultaneously developed and published. For historical reasons, we will use the name ROPA in this work. The main contribution of this paper lies in its case study. It's the first reported implementation of ROPA in an actual system. The system of interest is a lab-scale rig that emulates a subsea production system. The main results are that by avoiding the need to wait for steady state, we increase economic performance while decreasing the variability between different runs. That means that we can expect ROPA to have a more consistent performance if the plant disturbance scenario repeats itself. The downside is, of course, that we need to develop a dynamic model and tune the dynamic estimation. Here is a short outline of the presentation that I'm going to start now. First, we're going to introduce the subsea production system. Then we're going to talk about the experimental rig and how it emulates this subsea production system. Finally, we're going to show some results, experimental results, and end the talk with some final remarks. In a subsea production system, you have a reservoir under the seabed that contains a mixture of oil, gas, and water. A well connects the reservoir to the subsea installations, which in turn are connected to the topside facilities by a riser. The riser is usually a very long vertical pipe. In the Norwegian continental shelf, for example, it can be around 300 meters long. In Brazil, where we have deep water production, it can reach up to 3,000 meters long. The fluids are driven from the reservoir to the top facilities by the reservoir natural pressure. In some cases, this pressure is not high enough, so we need an artificial lifting method. One of the alternatives is to use gas lift. Here, in this slide, we show a different scheme of an oil well from the previous slide, but it shows basically the same thing. A well connects the reservoir and a riser connects the well to the top facilities. The idea of gas lift is simple. We add gas at a given point of the well. As a consequence, the bulk mix density decreases and the hydrostatic pressure also decreases. Then we can increase the production even with a low reservoir pressure. The catch here with this artificial lifting method is that we have a trade-off between hydrostatic pressure and friction pressure loss. As it can be seen from the plot on the right, where we have the gas lift in the x-axis and the production in the y-axis. After a given injection flow rate, since there is too much material inside the pipeline, the friction effects dominate the density decrease effect, and the production decreases instead of increasing. Clearly, this scenario can profit from an optimization method to find the best injection flow rate. The things get even more interesting if we have a well network. Then we have different wells with different productivity indexes, and a limited amount of gas to inject in the system. This constraint on the gas availability comes from the fact that the injection gas is the gas that is produced in the wells, compressed, and re-injected into the system. Therefore, it's natural for ourselves to ask the question, how do we optimally distribute the gas lift among the wells? For making these decisions, we want to apply both production optimization methods that were described before, the classical two-step RTO and ROPA, where an extended Kalman filter is used in the dynamic adaptation layer. So, as I said, the main contribution of the paper is that we carry out the first ROPA implementation in an actual system. Here is a picture of the rig. If you use your imagination, you can see the wells on the seabed here and the risers on the right-hand side of the picture. Since it's a bit hard to explain what's going on here because of the wires and the pipes, let's use a simplified scheme. In the rig, we have a system with two wells in parallel. The fluids that we use are water and air. Despite not being the same fluids as in a real oil well, we can see the gas lift effect, and it makes our life easier and cheaper to operate with water and air. The rig is composed of three sections: a riser section in which you have a water tank, a pump, and two control valves. This configuration allows us to emulate these different reservoir productivity indexes, for example. Then we have the well sections where gas is injected by two control valves, and finally a riser section where two vertical pipelines of 3 meters high in this case enables us to see the gas lift effect. For environmental purposes, the water is recycled to the water tank. Regarding the optimization problem, we want to find the set points of the air injection valves that maximize the system production while accounting for a price on the air compression. As mentioned, the problem is subjected to a maximum gas availability constraint. The maximum gas availability threshold was arbitrarily defined. The prices, however, were chosen such that we represent that the oil revenue in such systems is way larger than the compression cost. To make the situation more interesting, we changed the valve reservoir openings with time to emulate a decrease in the well's productivity. Therefore, the production optimization methods have to track the system optimum during the experiment. So, as I said, the valve openings profiles here represent different reservoir production indexes. When the valve opening decreases, it indicates that the well is depleting. Since we don't exactly know what the optimum is here, we had to use engineering intuition to determine which is the expected behavior of the production optimization methods. I'm not going to go into too many details here, but in between 0 and 5 minutes, it's expected that more gas is injected in well 2. Since there is less material inside and the oil production gain with relation to injecting 1 unit of gas is larger here. Near the end of this scenario, it is expected that the methods balance the gas lift more equally between the two wells. So now let's check out the experimental results. On the top plot, I show the same valve opening plot that I showed before. The plot in the middle is the gas injected in well 1, and the bottom plot shows the gas injected in well 2. We plot the decisions of the two-step RTO in red and ROPA's decisions in blue. Both are outcomes of two independent experiments. In addition to the gas availability constraint, in which the summation of the gas injection in both wells should be lower than 5 standard liters per minute, we also have upper and lower bounds in the gas injection. We notice that the gas distribution follow our engineering intuition in the plots. First, well 2 is favored, and near the end, there is a balance between two wells. Another thing that is easy to notice is the delay caused by steady state detection in the two-step RTO. The system takes longer to reach the optimum since the method updates the inputs, then it has to wait for the system to reach steady state again in order to update the inputs again. On the other hand, ROPA does that continuously due to the association of a dynamic model adaptation step. Also, note that around 9 minutes, the steady state is wrongly detected. Note that the disturbance on the top plot indicate that this around 9 minutes, we are not at steady state. Despite not being harmful here, this can be potentially dangerous in other systems. But in the end, what matters most is the obtained profit. The problem is that since it's an actual system, we don't know the optimum. Therefore, we use a fixed input solution for comparison, in which we simply divide the available gas equally between the two wells, independent of the disturbance. Since the measurements are noisy, are kind of noisy, it's hard to see anything here. So we created this index G bar, in which we compute the profit obtained at every time instant, calculate the difference in percentage to the fixed input approach, and then calculate the average. Here, we see that by simply choosing a smarter gas distribution, even with all the delay caused by the steady state detection, we improve the results by 4% approximately. Then, by adding ROPA's dynamic model adaptation component, we get an extra 1% improvement. However, one could argue that we have been simply lucky and gotten good results in a special run. Then, what we did, we had 4 independent runs of each method and then calculated the total profit, which is simply, for example, if we look at the plot on top, is the area under the curve here. And next, what we do, we computed the average of the 4 runs and also the standard deviation of the cumulative area of the 4 runs. We see that indeed, ROPA has not only a larger cumulative profit in average, but also a lower standard deviation, indicating a more consistent performance. The final remarks of my presentation are, here we report the first actual ROPA implementation. You can find many more details about the implementation in the paper. Here was just a brief description of the main results. The results that I showed here indicates that in the system there is an advantage of using dynamic methods, but this comes with a cost. You have to develop a dynamic model and of course tune the dynamic model adaptation step. We also concluded from the 4 independent runs of the classical 2-step RTO that the steady state detection method can be the main source of variability of the 2-step RTO. Finally, as further work, we plan to apply different production optimization methods to the rig, such as modifier adaptation and extremum seeking control. With that, I would like to end my talk. Thank you for the attention and leave my contact if someone has any questions. Please, if you want to reach out, just shoot me an email. I'll be very glad to reply. Thank you very much.